Hello, welcome. Today we're going to be solving Laplace's equation on a disk. So recall what we mean by this. And really what we're doing is using polar coordinates. So what we mean here is that we have a disk, a circular shape, and we'll always put it at the origin. So every point here, we have an unknown function u of r theta. That's theta, and that's the radial distance from the origin. So we can assume this circle, we'll assume this circle is r radius. Okay, so let's solve this thing. So the key points here is Laplace equation then is going to be the Laplacian of u is equal to 0. And from the previous movie, if you bother to watch it, it was the Laplace in polar coordinates. The Laplacian is going to be 1 over r times the partial of r, all of r times the partial of u with respect to r, plus 1 over r squared partial of u, second partial of u with respect to theta. Okay, and so there's that, and then we have a boundary condition, and the boundary condition is then that u at r is equal to the outer radius, theta, is equal to some function f of theta, where f of theta is periodic. That is, f of theta plus 2 pi is equal to f of theta. Okay, for any theta. In our domain. So the idea here is, if I was going to kind of put this disk on its side and assume here would be our u axis, on the edge of this this outer circle here of radius r, we have some known potential for u. And again, just like usual, we want to know what the surface looks like in the middle. We want to know what that u is. So we're going to solve it today, and we're going to use our standard technique of separation of variables. The only wrinkle here is that we have our Laplacian now is this more complicated looking differential operator. But the thing to note about this is it's still linear. That is, if I have two functions, the Laplacian of the sum of the two functions is just Laplacian of the two functions individually. And if you go through this, you can verify that. All right, so let's solve this. So let's solve this. This is going to be, again, we're going to have the Laplacian of u, which is equal to 1 over r, and I'll put the partials like this. Okay, so again, right here in this lower corner here, that r represents the partial derivative with respect to r of what's inside of the parentheses. So again, as before, and again we have u at r is equal to capital R of theta is some given boundary condition. Okay, so with these two together, we're going to do what we normally do, which is guess that u of r is equal to Q R P of theta. Okay, so we always have our P's and our Q's, and then we're going to apply our normal trick of plugging it in. So, the Laplacian of QP is going to be, so Q is our function of R and P is our function of theta. So if we put U right in there, the P will pass right through all those derivatives of R. We have 1 over R times Q, the partial of Q with respect to R. And we have to take that derivative again with respect to R. And here we have Q on the outside of R times 1 over R squared P double prime. Okay, I'll get my notation straight here in a second. P theta, and that's going to be 1 over R. And what we have here is we have to do the product rule here. So we have Q prime, and that's going to be a derivative with respect to R, plus R times Q double prime with respect to R, plus QR times 1 over R squared P double prime. All right, so now we just have to, of course, we're always setting this equal to 0, and then we're going to separate now. So we're going to separate P and Q. So let's do that. So we have to move some things over to the other side of the equation, so we'll do that. So we're going to have our P and our 1 over R Q prime plus R Q double prime. And that's all going to equal minus Q 1 over R squared P double prime. So I'm going to divide by Q here and divide by P here. And while I'm at it, I'll also multiply both sides by R squared. Okay, just to simplify things a bit. So the P's cancel here. We have to put a P down there, and we have to divide by Q for both sides, actually. Sorry about that. Always got to mind your algebra. Do it right. And then here, the Q's again cancel, and we're left with 1 over Q times R times Q prime plus R Q double prime. That's a times there, is equal to, and here we're going to have the cancel of those R square, and we're just going to have P double prime over P. We have a subtraction symbol there. Okay, we're almost there. I'm going to go a little further here. Just distribute in some. Well, actually, we can pause for a moment here, and just note that we can set that again. Again, this is a function only in R, and this is a function only in theta. And so when we have two sides that are equal to each other, yet they're functions of different variables, independent variables, we can set them equal to some unknown constant. And then what we can get is two separate equations. The first equation is just the standard one that we've seen many times. P double prime is equal to negative lambda P. Okay. Again, that's our theta equation. All right, and the second equation looks a little bit more complex. We're going to write that out, and that's going to be, oh, you know what we did? We forgot our R. No, we didn't. We're good. Okay, so we're going to write this down as going to be R squared Q double prime plus R Q prime minus theta Q is equal to 0. Okay. So this equation, and this is again our equation in R, like so. All right, so let's see if we can solve both of these equations. And like usual, we're going to solve this one first, and then that will help determine our R. So as before, we had P double prime is equal to negative lambda P, and this is of theta. All right, so what we know about this equation is it has some very nice solutions. So first of all, because f of theta, our boundary condition, is periodic, then P is periodic in theta, then P of theta must also be periodic. Okay, so we know then that P of theta has to be some C1 cosine root lambda theta plus C2 sine root lambda theta. And we know then that it has to be periodic, and not just any periodic, but 2 pi periodic. Okay, so 2 pi periodic, and that means then that that square root of lambda has to be n, right? That's the only way to make cosine and sine both periodic, 2 pi periodic. That is, we require that that square root of lambda times 2 pi has to equal sorry, I'm going to rewrite this. That square root of lambda pi must be the same angle as sorry, I'm misspeaking here. Should just go back and actually I'll just erase this. Nothing more needs to be said about it besides that when theta is equal to 2 pi, that the product together with our square root of lambda has to be some multiple of pi. So it has to be some multiple of 2 pi. So so that means you have to have, you're restricted to values, integral values. Okay. So with that established, then of course we can say that lambda squared is equal to n. Sorry, lambda then is equal to n squared. It looks pretty good. All right, and we see that both sine and cosine are both valid here. Okay, so that looks very interesting. Okay, so what we're going to do then is say that we have our family of functions now, Pn. Well, we should rewrite this a bit. Really, the solutions are the set cosine n theta and sine n theta. N equals 1 to infinity. But there's one more solution. It's going to be union the solution of just 1. That is also a solution here, right? That will be a periodic function as well. So we have both of those. All right, so that's nice. Now let's go on to the other side of the equation. That was a little bit more complicated. So, so that equation again was r squared q double prime plus r q prime minus, and now it was lambda, so that'll become n squared, q equal to 0. So without going too deep into this does have solutions. The solutions are Qn are equal to C1 Rn plus C2 R minus n for n greater than 1, and Q is equal to, when n is equal to 1, this is going to be C1 plus C2 natural log of R. All right, so sorry, no, what I mean here, this should be for n greater than or equal to 1, and that should be 0. Okay, so for Q 0, so this is for n is equal to 0. But we want U of R equal to 0 theta to be bounded. So we can't have any natural log solutions, and we can't have any inverse powers. So what we're left with then is simply Qn is equal to Rn, and then we also have constants. Just that's one set of solutions. Union, and then we have this constant here, just C. We can just call it 1. Of course, we can take any linear combination of these solutions to create new solutions. All right, so these are the solutions in theta, and these are the solutions in R. Of course, we put them together, and we get Un R comma theta is equal to, it's going to be equal to something of the form An times Rn cosine n theta plus Bn Rn sine n theta. All right, I'm also going to put an A0 out there. I'm going to put a plus, and might as well just add these all together right here. So any solution is going to be the form n is equal to 1 all the way to infinity. Now, we're playing fast and loose with that infinity. We're assuming that this series converges. But divergence issues notwithstanding, this is an adequate solution for us, provided that converges. So our U then has a really nice form. It has a Fourier series, or a trigonometric series in there. But now we have these functions. So sorry, that should be a r to the n power. We have these functions of r to the n power there. Okay, so that looks good. Now we have a way of solving for our answer. So now let's just finish this out. Okay, recall our boundary conditions. So our U of R theta is equal to, again, A0 plus the sum n equals 1 to infinity of An R to the n power cosine n theta plus Bn R to the n sine n theta. I'm going to put that all together like that. Okay, and we recall that the boundary condition is R is equal to capital R of theta, and that's going to become A0 plus, and that, sorry, I'm going to rewrite that again. We know the boundary condition states that when we evaluate R as little r is equal to big R, the outer edge of our disk, that's going to be f of theta. We can evaluate that then as A0 plus integral n equals 1 to infinity An Rn cosine n theta So we have to put an R in there, plus Bn capital R n sine n theta. Okay, so there we go. So now we have a way of computing the Fourier, or the trigonometric series, which we call the Fourier series, for our boundary condition. And so, just as you may imagine, A0 is simply going to be f inner product with the function 1, like that. That'll be our orthogonal projection onto constants, and an will simply be, and here we have to do a little trickiness here. We have to remember to divide by Rn there, and then just as before, f cosine n theta over the inner product of cosine n theta with cosine n theta with itself. And likewise, Bn is equal to 1 over Rn times the inner product of f with sine n theta all over the inner product of sine n theta with itself. Okay, so those put together. So now let's do an example. I'm actually going to pick out a very specific example. So we'll say that a(n)s are all going to be equal to 0, but for n greater than 1, or greater than or equal to 1, and a0 itself will be 1. And we'll say that b4 will be equal to we'll say it's equal to 1 over 2 to the 4th, and we'll say that our capital R will be equal to 2. We're going to have a radius 2. And so that implies then that our solution u r of theta is going to be equal to it'll be equal to 1 plus r squared, sorry, no, apologies, r to the 4th power sine 4 theta all over 2 to the 4. Okay? So with this solution here, we can actually plot what this looks like. So again, the boundary condition for this then, if we can't see it here, is if I put r is equal to capital R, which is equal to 2, which will be f of theta is equal to 1 plus sine 4 theta. All right, so that's the boundary condition. So now let's see what this looks like. So clearly, as r gets smaller than 2, we expect that this function is going to get smaller, because small numbers to high powers will become smaller. So numbers smaller than 2. Okay, so let's actually, I plotted this function, so let's show it here. So there it is. All right. So we can see pretty clearly that on the boundaries we get a periodic function that oscillates 4 different times, and that's because there's that sine 4 theta. And we notice that it goes up and down really wildly on the boundary, but in the center things sort of calm down a bit. Okay, so it's a little bit more flat, a little bit more subdued at the center. All right, so that, of course, is an important property of the Laplace equation, which represents a steady-state temperature distribution. That if you have extreme temperatures on a boundary, the mixing of heat flow in the interior heat-conducting region is going to sort of even out things a bit. It's going to sort of average the exterior temperatures and find some intermediate value. And in later videos, we'll establish that property more formally. So thanks very much.